Hello and welcome to the presentation on biochar and circular economy, specifically focusing on use of biomass feedstock contaminated with plastic for biochar production and the impact that this plastic contamination may have on biochar properties and biochar applications. I would like to thank the organizers for giving me the opportunity to present our research here, and I would also like to thank my collaborators whose research is presented here and without whom none of this would have been possible. So to first briefly introduce Edinburgh and the University of Edinburgh, you can see a few nice pictures of the city of Edinburgh, and it's a very historical city, and the university is based right in the center of it. The University of Edinburgh is based on a number of campuses. Here we can see the central campus with the so-called Old College. It's a university with 33,000 students and 6,000 staff, and a number of famous alumni, both historic and recent. I represent the UK Biochar Research Centre, which is based at the University of Edinburgh, and I'm one of the co-founding members of the centre that started back in 2009, so it's been around for around 12 years. It's a multidisciplinary center that brings together expertise in areas of technology. So that's the area I lead in terms of pyrolysis technology and thermochemical conversion technologies for biochar production, but also soil science, environmental science, social science, and so on. So we are tackling a lot of different aspects related to biochar production and different applications of biochar and its performance in those applications. At the UK Biochar Research Centre, we operate a number of facilities for biochar production research, and you can see here on the slide 4 examples ranging from very small scale, so thermogravimetric analyzer, where we can process a few tens of milligram of material, and then several small laboratory units that can produce anywhere from few gram to few tens of gram or perhaps few hundred gram of biochar. And also the so-called stage 3, which is our pilot scale facility, where we can process up to about 50 kilos of biomass per hour, so producing tens or hundreds of kilos of biochar per day and tons of biochar per week or so. All these production facilities can operate at a similar range of conditions in terms of the temperatures, so that we can reproduce biochar from one scale at the next scale. So and we have already shown extensively that we can produce similar biochar on what we call here the stage 1 unit and a stage 3 unit, so we can really scale up the production of biochar while maintaining the same properties of the resulting product, which is very important. All these production facilities are accompanied by state-of-the-art research and characterization facilities, both at the School of Geosciences, where we are based, but also other schools within the College of Science and Engineering. And you can see here examples of scanning electron microscopy, but also ultra-high resolution mass spectrometry for characterization of compounds evolved during pyrolysis, and so on. Now, as you already know, biochar can be used in a lot of different applications, and here is a diagram that lists quite a number of them in a lot of different areas, such as soil, in agriculture, horticulture, in water treatment, electrochemical applications, and so on. There is also the potential to link a number of these different applications, and that's what I'll be looking at in the next few slides. So here we have a concept that we call the sequential biochar system. It is a concept that we've been developing as part of the EU-funded project Green Carbon. It's a project that's now coming to an end after more than 4 years of running. And here you can see the concept where biochar is used not only for one application, so producing biochar and then, let's say, applying it to soil to serve a specific purpose. What we are trying to do here is to find sequences where we can use biochar for one thing, then another, and then perhaps another one. So the sequence can include 2, 3, or even more steps, depending on what those steps are. The key thing here in this concept is that in the ideal sequential biochar system, every sequence adds a value to the biochar before it's used in the next step. So rather than degrading the value of the biochar, so the biochar losing its value with each subsequent use, we actually are trying to find sequences where the biochar gains and improves its value. And I'll show that on the next slide. So here we have two examples of sequential biochar systems where we can see a biochar being used in three different steps before its final application in soil. In the first example, biochar is used for removal of sulfur or hydrogen sulfide from biogas. Then the sulfur-enriched biochar is used as a sulfonated catalyst in esterification before use as a pH buffer in composting and final storage in the soil. In the second example, biochar is used for phosphorus removal, for example in wastewater treatment. Then this phosphorus enriched, so nutrient-loaded biochar is used in composting, and again before final use in the soil, where the phosphorus can then be released and available to plants. So you can see that each of the steps here improve the biochar for the use in the next step. The aim of this concept is to both improve the environmental performance of biochar, so we can address several environmental problems with the same starting material, but also because we are using one material for a number of different applications, we can share the costs of the production of that material among those different applications, and that's what's shown in the schematic at the bottom. So the cost associated with production related to the biomass feedstock, the conversion technology, transportation, storage, and so on can be split among those different applications. We can use a lot of different types of biomass for biochar production, and here we can see the two main types, so-called virgin biomass, which is biomass so as produced or as grown, which typically is characterized by higher cost and high competition for various uses of it. The second type is a non-virgin biomass that typically has a lower cost, but also has more challenging properties and has possibly less competition because of those challenging properties. So there are different options. One of those challenges that we can face here is also presence of contaminants, and that's what we'll focus on here in this talk. So there can be a lot of contamination issues related to both feedstock and the conversion process, and they are listed here on this slide. But in this talk, I'll focus mainly on the microplastics and talk a little bit about some of the hydrocarbon-based contaminants, so polycyclic aromatic hydrocarbons. The nature of microplastic contamination of the biomass stream will depend on the origin of the contamination. As you can see here on the picture, there are a lot of different types of microplastics ranging in shape, size, composition, and all of this will have an impact on the properties and on the conversion process when we produce biochar from these materials. The two materials I would like to mention here specifically are anaerobic digestate and also sewage sludge from wastewater treatment. These tend to contain a large amount of microplastic because of the origin of the source, where the microplastic coming from different streams accumulates and is concentrated in this final product. So based on research to date, we can conclude that there are thousands to tens of thousands of microplastic particles present in a kilogram of dry sludge, and because of the still very common application of sludges to soil in European agriculture, tens of thousands to hundreds of thousands of tons of microplastic end up in the soil in Europe every year. So this is a challenge that needs to be addressed, and it's a growing issue and growing concern. So the first example, or the first case study I want to discuss, is anaerobic digestion. That's a common process used in farms and various other industries for treating organic residues such as food waste or manures and so on. There is also a very good potential of linking this biological treatment to thermochemical treatment such as pyrolysis, as shown on this diagram. And the reason for doing that, there are multiple reasons for doing that, as shown here. So four-way synergies as indicated here, and I'll very briefly mention all 4 of them. So the first one is the use of the solid residue that comes from the AD process, and that can be used on farmland as it is, but again, already as mentioned, the contamination with microplastics can be an issue, and farmers might not be or might be resistant to apply this type of material of contamination to their soil. If we process this residue in a pyrolysis process, we can produce biochar, and as I will show later, we can completely decompose all the plastic and end up with a plastic-free biochar that can be used on soil. Another potential synergy here is to use the biochar actually in the AD process itself, and it has been shown that we can increase the methane yield considerably, boosting the revenue of the AD plant because of increased production of methane with only minimum addition of biochar. Another option is addition of the liquids from pyrolysis, and that can be either only the aqueous fraction, which is the light yellow liquid here, or the tarry fraction, the dark brown liquid, that can be fed back into the AD process, and after some adjustment of the microbial community in the AD reactor, this can be decomposed and producing more methane. And finally, the gas from pyrolysis can also be fed back into the AD process and converted into more methane. So there are a lot of interesting synergies there, linking the thermochemical conversion to biochemical conversion. What the thermochemical conversion also does, it can help us to deal with the issue of microplastics in the AD digestate. Here on the schematic, I'm just showing conceptually the flow of microplastics coming from different sources in agricultural residues, where it should be less of a problem, but also municipal solid waste or food waste, wastewater treatment sludges that come contaminated with microplastics. In the AD plant, because of the decomposition of the organic matter and retention of the plastic that does not decompose there, the relative concentration increases, and therefore the digestate contains a higher percentage of microplastics than the materials that we put in, just because of the simple concentration due to the loss of organic matter. And if this is applied to soil, we are applying material that contains a lot of microplastics. Therefore, we can do a thermal treatment, we can pyrolyze it at sufficiently high temperature and sufficiently long residence time, producing biochar that contains zero plastic contamination. So we have a safe biochar, at least in terms of plastic content. And here is a graph showing the yield improvement of methane with application of biochar. If you want more information, I'm happy to provide that, and we have also some published work on this as well. This technology is now being commercialized by a spin-out company called Carbogenics, which again you can look up online. Another example of biomass contaminated with plastic is biomass coming from peat-based growing media, and these often come packaged in plastic bags, which at the end of the use need to be disposed of. What we wanted to see here is whether it's possible to pyrolyze the material, the organic material, together with the plastic, which saves a lot of labor and cost in terms of depackaging. And we wanted to see whether this would have any detrimental impacts on the process itself or the quality of the resulting biochar. So that ideally we can have a process that operates in this cycle as shown here, where the spent media can be used for producing ingredients for the new growing media without any issues with contamination. So we have done, we've pyrolyzed a number of different growing media with different type of plastic at different concentrations, and we then analyzed, did extensive analysis of the products and wanted to see what type of contaminants there are in what concentrations, and then compared it to the International Biochar Initiative standards. And the results look very promising. We have shown, as you can see here on the slide, that the presence of plastic, and we worked with concentrations up to about 2.5%, which corresponds basically to the compost or the growing media in a plastic bag. So that's the right ratio. Had no negative impact on the quality of the biochar itself. In some cases, it actually resulted in a better quality biochar. In any case, all of these met the criteria of the International Biochar Initiative in terms of contaminants present in the biochar. So we can conclude that this type of processing is suitable. It not only destroys any diseases that may be in the spent growing media, it also removes any issues with plastic contamination. As part of the work, we also did some plant trials, so looking at what impact this would have on the plants. So it's not only about what contaminants there are or there are not in the biochar, we also wanted to see whether this has any impact on the plants. And again, the studies showed that there is no negative impact. We can safely replace part of the growing media with biochar up to about 50%. We found that at 23% volume per volume replacement, we had the best performing growing media, performing better than the original growing media. And at up to about 35 to 47% peat replacement, it performed in the same way as the original growing media. So again, an interesting and encouraging set of results. So in conclusion, I would say that there are a lot of different applications of biochar, and there are a lot of potential synergies between different applications. So the concept of sequential uses of biochar that really offer a lot of opportunities in circular economy and make biochar more economically favorable and also with better environmental performance. And finally, plastic contamination in biomass streams is not necessarily a problem for biochar production. It's not to say that there can't be cases where it is a problem. It very much depends on the nature of the contamination. So what type of plastic it is, and does it have any components in it that could be problematic, such as heavy metals for some special type of plastic. But in general, it is not a problem if properly converted. So again, the conversion system, the biochar production process, is very important so that it's operated in the right way under the right conditions, so that no contaminants are retained in the biochar. Therefore, we can produce clean biochar even from contaminated feedstock. So thank you very much all for your attention. If you have any questions, I'll be more than happy to answer those. Here are my contact details. You can either scan the QR code or they are here on the slide, and I'll be more than happy to have further discussion with any of you who may be interested in the work I presented here or other work we do. So thank you again for your attention.